Okay, everybody. I think now might be a good time to get started. I'm super excited to get to introduce Sabrina today. So Sabrina is a PhD student at Johns Hopkins University, and she's currently researching open vocabulary language modeling for vocabulary selection and unit discovery. While her pre-PhD work focused on formal language theory, during her PhD, she's published on a variety of NLP topics, together with colleagues from Google AI, Facebook AI Research, and Hugging Face. Thanks so much for being here with us today, Sabrina. I think you're muted, by the way. Okay, Sabrina's going to rejoin us in a second.
Again. There we go. That should do it. Okay. Here we go. That's better. Cool. So first of all, I did for interactivity in this make a Slido. So if you've used them before, you know how it works. Otherwise, you go to slide.do and enter this code, and then you should be able to ask questions and answer questions that I put out. So let me know if that doesn't work. It should work, I hope. Somebody raised their hand. Where do I have the chat? Here we go. Was there something? Otherwise, I'm just going to leave that open and we'll see how it goes.
Mohib, you can unmute if you want.
Maybe if something comes up, we can look at that again. So let's just get started. So you should have by now have been exposed to a ton of lectures in the school and heard a lot of things. And maybe you're somewhat overwhelmed. I don't know, I know I will be. So this being the last lecture that is sort of the technical introduction to new concepts, might be also having all sorts of feelings. I will say that if you haven't been following the last lecture so much, hopefully this lecture will be a chance to kind of jump into something new and start without needing so much of the previous stuff. That said, I will hope that you have a sense of what neural networks are and you know, what is a convolution layer and all these things. So hopefully we're kind of on the same page. Yeah, again, let me know if you have any questions. You could raise your hand, unmute, put it in the chat, put it in the Slido. There is certainly not a shortage of options. All right, so an intro to NLP. That's sort of a lot because I mean, yeah, NLP is an old field, well, reasonably old for computer science, I guess. It's existed for numerous decades. It's gone through so many paradigm shifts, and even just looking at what is happening today, there's so much that one could talk about. So I was like, okay, well, what exactly do you want to focus on? That's especially true because, I mean, if you look at these statistics for like how have NLP conferences grown, it's the same image we see in other AI-related fields. There has just been this really stark growth. So yeah, there's a lot to talk about. And the way that I want to do this today is kind of attempt to give you something that I think exposes you to a lot of things. And from then on, we'll open up and kind of let this lecture go how you want it to go. So what we're going to be doing is I have a bunch of slides that will probably fill the first hour, and then we'll see what else we're up for, what you're interested in. So I have a list for that too. We'll get to that. So what we're going to be doing in this first part is kind of jumping from image classification, which you've seen, to text classification, which is going to turn out to be somewhat similar, but have its own kind of interesting interesting quirks. We're going to look at n-grams as sort of an old school way of doing NLP, but then just quickly move on to distributional word representations or word embeddings, which you might have heard of, and which are definitely, you can't think of NLP without word embeddings anymore. We'll try to build an end-to-end model for classification using convolutional networks and pooling. So that's going to be nice to see that back in action. And then jump to what is now the most commonly used architecture in NLP applications, the transformer, and talk a little bit about self-attention to bridge long distances. That'll lead us to talking about generative language modeling, which, as you might have it, is my favorite topic. Oh, wonder why that's on the slides. But it's also going to be very relevant because many of the big advances in NLP have been generative language models, and we see we're going to see these interesting results from that. And finally, we're going to talk a little bit more about how to generate text using generative language models, talk a bit about sampling, before opening up to a bunch of other topics you might want to dive into deeper. So just really quick, you already introduced me. Thank you for that. I am a PhD student, hopefully soon finishing, maybe this year, or fingers crossed. And I did my undergrad in Germany. I did a bunch of stuff in formal language theory, theory of computation, which at the time looked like it might have a little bit more to do with NLP, because NLP was a lot about grammars and automata and those kinds of things did appear, although that, of course, then changed in subsequent years. And so during the PhD, I published on a bunch of things in NLP, on translation, morphology, creating resources, language modeling, because it's my favorite topic, comparing models fairly, chatbots, and just recently we've had a survey out on tokenization. So I'm kind of all over the place, but maybe that'll be nice for a lecture. Okay, so let's just jump right into it. We have seen image classification in previous days. Yesterday, just I think in the computer vision lecture. So okay, we can probably think that it might be a nice idea to start doing that with text. What would it mean to classify text? Well, you could have some examples, like imagine you want to classify documents that are news articles, and you want to classify them and say it's about sports, this is about politics, this is like a comment. That will be a classification task. We could think of other ones. We could think of social media posts. You could classify those in all kinds of ways, and many of them are probably bad ideas. Like if you want to classify gender, maybe don't. And, a bunch of other things you could do. I don't want to get into that too much because I know some people are doing interesting and good research with social media posts. Or we can look at movie reviews, for example, and that's the example we're going to be running with for these slides, and I think also for the lab this afternoon. You could say the classes are like 1 star, 2 stars, up to 5 stars, or maybe positive, negative. In these slides, we're just going to do like a 3-way classification: positive, neutral, negative. But okay, so I hope you kind of buy that this is a thing that makes sense to do, to classify text as we did classify images. So how are we going to do this? Any ideas? The title kind of gives it away, but the first idea, maybe I'll just open with that. The first idea might be to say, look, if we have this thing and it's like something about a movie, maybe there's an adjective in there that says amazing, or something that says terrible. Maybe we just want to look at the words. If we want to look at the news classification thing, then maybe if the word ball appears in a text, we want to have a rule that says, oh, there's a ball in there, therefore it's a sports article. Can anyone see what's probably going wrong with this one? Yeah, there could be all sorts of things that have the word ball. Exactly. We could have drop the ball, a gala type ball. There's so many things, right? If I say, or pass the ball, well, this is clearly, this excerpt is not sports, and that would be a strange name for a sports team. So we probably don't want to have these simple rules. So maybe we can come up with something more complicated. Does anyone have an idea how we could make this a little bit less extreme? Like, oh, if there's a ball, it's always sports. Well, maybe we can soften that. Does anyone have an idea how to maybe do that? The words used together is going to be, and words in context, that's going to be a really useful thought in just a minute. Yeah, something about frequencies and probabilities. That's probably a good start. I'm going to propose to do something that is not a strict, hard and fast rule, but something that is like a soft rule. Like maybe we can say we're giving points to all the possible classes. Say we have sports and politics and comments. And so we can say that seeing the word ball gives a few more points to the sports category, so it makes it kind of likely. But then seeing the word Republicans gives a lot more points to politics. So even though there's some evidence for sports, there's more evidence for politics, so we're going to choose politics. So that's something we could do, right? And that solves the problem somewhat of hard and fast rules, but it still is kind of messy. And as you said, the word ball, if it appears in like constructs as pass the ball or drop the ball or gala ball, well, we should really look at those. We should really look at bigger things, right? So keep that in mind. Before we go there, one thing that can be left unspoken that I think we should spell out is that if we want to have these soft rules, really, who said that it was going to be 0.2 points or 5 points? We probably don't want to write those by hand. I mean, we could, but if we want to be cool and like enter the 90s, where of course science was amazing, we're going to have to learn these automatically from data. So we're going to take a bunch of documents of sports, take a bunch of documents of news, and then just see, yeah, how often do certain words co-occur in these topics. Maybe we'll do, if you've heard of TF IDF, that kind of stuff can definitely be helpful here. And that's how we sort of get these numbers. We learn them from data. And that's, of course, what we're going to be doing and all of what's happening and what you've been seeing the past few days. And you talked about regression. That's exactly that happening. But I figured it would be good to just spell that out. Even in these simple rule-based approaches, we are doing some learning. So these two schools of thought are kind of interesting because I think they're exemplary of what NLP used to be decades ago. The first one really being this rule-based NLP, where you have very complicated rules that could say something like, if there is ball in the text, but there is not Republicans in the text, then output sports. And you have these really complex systems built by humans that are really brittle. And then the second one, the jump to statistical NLP in the 80s, 90s, where we really want to learn soft probabilities and scores from data, which was controversial at the time, but today feels very old-timey in a way. Okay, so these are some naive attempts, but we want to do better, right? We already have had a sense that language is a little bit of complicated, like ball does not mean ball. And I want to give you an example that really makes that clear. And that's the example of negation. So if we take this movie review, the movie was hardly amazing, really. Well, if we want to zoom in on words, then amazing, well, sounds like this is a good movie review, right? But clearly that's not how it works. And hardly amazing, really, it's not amazing, it's anything but amazing. So that should be a negative review. But how can we tell? Like any individual word doesn't really tell us anything negative, right? Hardly by itself, well, that could mean anything. I could say they hardly break a sweat as they make an amazing movie, but it doesn't necessarily say positive or negative. A single word here really is not enough. It's about these two words, hardly amazing, together, that the negative meaning emerges. So there's really something in here about the sequence. And you can see this if I just take the sentences, take the sentence, reorder the words, and get this review. Imagine a movie called Hardly. I don't think there is one. I looked it up on IMDb. I didn't find one. But imagine a movie called Hardly, and then you could say, "Oh, the movie, yeah, Hardly, the movie was amazing," and now it's a positive one. So the sequence really matters. And what we've done here, when we said we are just going to look at the individual words, is we have made a so-called bag of words assumption. So we're assuming that a sentence is just a bag of words, like a set, but things can occur multiple times, and there's no order information. And that's probably not the best kind of assumption. Now, it is an assumption that makes things easy, right? We didn't have to worry about order, where a word appears, where other words appear. So that made our lives really easy. And so there are good reasons to sometimes make this bag of words assumption. But yeah, it's not great. It's not great. And it really fails on this particular example, which you would assume you would see a fair share of in movie reviews. So sequence really matters. So here's the next idea. Let's say we don't want to look at the indicative words, but look at indicative n-grams. And n-grams really says a string of multiple words together. So like a 1 gram would just be one. Strongly positive, not amazing, that's strongly negative. Hardly amazing, that's also negative. Oh, is it lagging?
Yeah, Sabrina, I think you froze for a few seconds. Would you mind maybe just going back like a couple sentences?
Okay. Where did I freeze?
Yeah, like
N-grams.
yeah.
Okay, sure. So if we want to say the sequence matters, and hardly amazing is a different thing than amazing hardly or something, maybe it makes sense to not look at a single word as indicative, but as like collections of words as indicative. And so that's what n-grams are. N-grams really being a string of multiple words. We can have a 1 gram, that's just one word, a 2 gram or a bigram, as we then call it, which is 2 words, a 3 gram, a trigram, 3 words, and so on. And so here we would have some n-grams that might be useful for this task. We got a unigram, a 1 gram, amazing. It's like weakly positive. Really amazing is a bigram, that's very positive. Not amazing is negative. Hardly amazing, also negative. And so now that kind of works, right? That kind of gets us this example correct, because now we see hardly amazing as one bigram, as one unit, and we say, oh, well, hardly amazing is a pretty bad thing, so this must be a bad review. Whereas if we just see amazing by itself with nothing interesting in front of it, we'd say, oh, that's just amazing. No interesting bigrams here. That's positive, I guess. So the n-grams really help us tackle this example. Does that make sense to people? Do you feel like, does it feel like, oh yeah, I could have come up with that? That's usually a good sign that you understood what's happening. Cool. Okay. Yeah, so n-grams were really a dominant thing in NLP for a long time, basically all the way up to the neural networks revolution, just like what, 6 or 7 years ago, something like that. So it's useful to know the concept of an n-gram, and people just like to talk about their bigrams and trigrams and tetragrams, I think. Not sure. You don't hear that one that often. But that's maybe an interesting question we could think about. How large do these bigrams get? Well, we can have unigrams, bigrams, that's reasonable. We can have trigrams, 3 words. I can see that being good, like not really great. No, it's probably useful trigrams. How long do you think we should make these? What do you think? How many words should we allow ourselves to have in our n-grams? So again, probably we don't want to hand code all this, right? Like we probably want the computer to find the n-grams that are indicative. And we want the computer to be like, oh, I found this n-gram and it's called really amazing. And it gives +6 because there's a high chance the document is a positive review. So quadgrams, yeah, we could go up to 4. Well, there's certainly things that take 4 things, right? Like not all that great. Well, before, that'll probably be good to have, yeah. You want to go higher? What do you think? How high should we go? Or is there an issue with going higher? Yeah, let ML decide. That's really the right answer, isn't it? So if you want to do this in practice, chances are you might want to have some sparsity, and you are just going to keep the n-grams that actually are indicative of anything, right? The n-gram the movie was, well, that's not a great n-gram. You probably don't want it. You probably don't care. But how large are we going to make these? Maybe a different question to ask is, what happens when we make them really large? What happens when I take a look at, say, a 10-gram? Well, it'll certainly increase the size of our model. We're going to have to keep lots and lots of those 10 grams in mind. But, say I only keep the ones that are really indicative. Yeah, they become too specific. That's the issue, right? They become so specific that they probably work well for like this one review that this one person wrote, and they're never going to be useful outside of that. So chances are we don't actually want the ones that are just so high because they appear very rarely. And that's not just a problem because it would be dead weight, not just a problem because it wouldn't be useful, but it's also a problem because it would be really hard for us to figure out, are these indicative of a positive or of a negative review? Because if it only appears once, and yeah, sure, it happens to be a positive review, does that really tell you that this 10-gram is useful for the positive review? Not really, right? Exactly. It would be considered overfitting. So we would overfit to this small example, this large example really, that we've only seen once or twice maybe. And that would really mess us up, because chances are that this has nothing to do with positive or negative. It just happened to be there. It just happened to only exist with positive reviews. Like maybe, hey, maybe there's like a saying that only makes sense in German, right? And you say, oh, let's look at this German thingy. And it turns out all Germans hate everything. And so all the reviews are negative. So now you think the saying has anything to do with negative. Well, that doesn't really work out. And chances are you're going to fall on your face when you try to apply that. So really, we have this issue of overfitting. If we have too large n-grams, we have so many different n-grams that appear so rarely, we get so little signal from the data, that's just really not a good thing to do. Okay, let's keep that in mind. We're going to come back to that in, I think, one slide. But this is an issue we're going to have to address. Okay. So we said, yeah, it could be we need longer things. But one thing I want to hone in on before we start building something is that, as the title of the slide probably suggests, there's a part 2. It gets even worse. Look at this sentence. The movie was not, as critics who had been looking forward to reviewing a movie which had been in the making for 10 years, hoped. Amazing, really. It's sort of a contrived example. What I'm trying to show is this combination of like not an amazing or hardly an amazing or really an amazing. And they don't have to be right next to each other. They could be far away in terms of the sentence. There could be lots of material in the middle. So if you want to catch that one, well, yeah, you really would need like a 10-gram or however much there is in the middle. And in truth, that could be arbitrarily much in the middle. Some people like to write long sentences. I love to write long sentences. So our n-grams are really not going to work here. So we have these arbitrarily long distance dependencies, what they're called. And yeah, n-grams are not going to do it. And that is why what neural networks gave us in recurrent neural nets and transformers now, which we're going to talk about, has been amazing. So no n-grams, but also n-gram sparsity issues that we've talked about on the previous slides. N-grams suck. It's the 21st century. We got to do something else. And we are going to do something else. And now we're going to be talking about how to build a text classification architecture with neural networks. And I already see in chat LSTMs and RNNs. With a heavy heart, I decided not to talk about RNNs in this presentation. Maybe we will after these slides, but you already know what's up. Good. Everybody else, we'll find out. So the central thing that we're going to have to talk about is how to turn words into numbers. And that's sort of odd. You might be like, why do we want to do that? Well, we want to do it to feed it into neural networks. Because what we've seen so far in neural networks in vision was pixels, right? It was like image data, and that is very much a bunch of numbers. These are arrays and matrices and tensors that you can perfectly fit into a neural network, right? You just look at the individual color channels and say, oh, this has 220 red and 100 green, blah, blah, blah. And you feed those numbers in and everything's beautiful. You just can't do that to text, right? Because like, what are the numbers that you feed into a network for text? It doesn't really make sense, right? The issue is that we have to go from these discrete words, which are really like their own units, which are not numerical, are not continuous, but we want to go to something numerical and continuous. And we're going to do that by thinking a little bit about similarity. So images are continuous, so similar things get treated similarly, right? If I change one pixel in intensity just a little bit, well, then everything downstream is hopefully going to change just a little bit. And with words, that's just not a thing, but it should be, shouldn't it? If I say something like, the movie was really amazing. Well, if I replace really by truly, I could say the movie was truly amazing. That's similar enough. It should be treated similarly, right? So can we do that? And the answer is yes, of course. There's space on the slide. Of course, there's something we could do. And that is we can actually arrange words in a way that shows us their similarities. So let's zoom in on that. For example, if we look at this cluster up here, this will be clustering like different kinds of meat together, which makes sense. And you see, I don't know how much you can make out, but other things kind of cluster together in terms of similarity as well. So that's something we can imagine ourselves doing, right? Like if we as humans wanted to turn words into numbers, we could probably draw a picture like this of like, where are words in terms of similarity, right? We could, I mean, how would we do this? Well, it'd probably be annoying, a lot of work. But let's take for granted for now that we can build this picture. Once we have this picture, we are done. Because now we just put a coordinate system on top of this thing, and we have word embeddings. So take the word lemon here, for example, it sits at -2 and 4. So its word embedding, its numerical representation, is the two-dimensional vector that has a -2 and a 4 in it. And that's what we can do to all these words now. And similar words will end up with similar embeddings. They're going to be close to each other, and their numerical values are going to be close to each other as well. Now, in practice, we're not going to want to be doing 2 dimensions, and we're not going to want to be the ones, oh God, who want to do this by hand. We want to have the computers do this on. So once we have this done, which we'll talk about in a second, we want to use more than 2 dimensions. So we might want to use something like 300 dimensions. And that's where things get really funny, because like we can imagine 2D, we can imagine 3D, maybe 4D possibly, but 300 dimensions, God, we can't even imagine how that works. But the math works out, and that's all that matters. But for the purposes of this, this slide deck, we'll be doing 2-dimensional word embeddings, which are not that powerful, but kind of get you the ideas and are a lot less effort to draw. All right, so how do we operationalize similarity? How do we get to this similarity image where we have words that are close to one another or not that close to one another? And sort of an iconic sentence that NLP people turn to explain why we have word embeddings is a statement by Firth, who said, "You shall know a word by the company it keeps." the company it keeps really being the contexts that it appears in. A word is sort of described by where it appears. What kind of sentences does it appear in? What kind of words appear in those sentences? What kind of neighbors does it have, right? We shall know a word by the company it keeps. So that's a good start, and we can probably do something with that. So what we're going to be doing is looking at these contexts. I have some very simple contexts here. For example, if we take the word cat, some contexts that might appear in might be something like the sat or my is. And you can think of many more contexts that it could appear in, right? And these contexts, by the way, don't have to be just one word to the left and one word to the right. It could be more than that, but I wanted to keep it simple for the slides. What was that? Oh yes, the company. Yeah, for sure. Yeah, there's some truth in that. I think it's an interesting sentence. Makes you think. Okay, so we can see that the word cat is characterized by, say, these two contexts. That's kind of true. The context tells us that a cat is something that sits, that a cat is something that could belong to a speaker. Okay, that's reasonable. But these contexts also characterize the word dog, right? The dog sat, my dog is, perfectly fine as well. Less so the word cow, like the cow sat, that's a little concerning. My cow is, I mean, some people have weird pets, but it's a little stretching it, right? And then when we have a word like green, well, that's definitely not going to fit. The green sat, my green is, unless you're tending to like a sports field, you probably are not going to talk about your green. So this is already giving us a sense of similarity. Taking these contexts, we can see that cat and dog are similar. Cat and cow are maybe a little bit similar, and cat and green are not at all similar. So that's going to be the idea that we can use to create these word embeddings. And we're going to just jump right into that. Now, as a word of warning, and maybe I shouldn't be saying this, but this slide and the next are completely useless for anything we're doing today, because we're going to do something different, much easier, but we don't have to think about it. But I think it's very useful to look at this technique, which is really an older technique called latent semantic analysis. Was it analysis or allocation? Shit, I forgot. Anyway, correct me in the chat, please. That is trying to find such distributional representations, find such word embeddings from this idea of words and their context. So how that's going to work is we start out with this big matrix, this big table of words and context. And the entries are going to be, how often has this occurred in some text that we see? So this is a machine learning method. We need a bunch of text. And then once we have a bunch of text, we can count these co-occurrences. We can count these word context pairs. Now, okay, we have this matrix. How are we going to get from here to word embeddings? Anyone know the magic word? I'm curious. How are we going to get from this to word embeddings? Just in case anyone knows, will be fun. Here's like, okay, so far I hope you're all with me that this is something we can do. This is something that a computer can do. You can write some Python code that generates this matrix. How to get from here to our beautiful similarity things? Well, the matrix is going to be real big. I mean, it's going to be huge. Imagine how many contexts there are, right? Even if we just have one left and one right word, that's still quadratic in the number of words. And that's going to be huge. And that's going to be too huge, right? We want many dimensions, yes, but like 300 is a good number. This would be like tens of thousands, hundreds of thousands of dimensions. Oh, we can't work with that. Word2Vec is, Word2Vec is using this idea in a slightly different way. So really only later research actually showed that Word2Vec was very similar to what I'm describing here. But good call. Anyway, the magic word is matrix factorization. So I hope you all paid attention in your linear algebra classes, because I know I did not in my undergrad, and I came to regret it. when I was in a computer vision lecture and the lecturer hit me with, here, now we take the SVD. And I was like, what is the SVD? Maybe that's you as well. So we're going to be doing this in relatively simple terms. What we want to do is express this matrix as a product of smaller and simpler matrices. And we can do that using this so-called singular value decomposition, which is just one way to decompose matrices. We're going to do this approximately and cut off some dimensions without going into too much detail. What you get is that this matrix is approximately similar to this small matrix. It's very tall. It has as many entries as words, but it only has 2 columns if you want to make 2-dimensional word embeddings. Diagonal matrix for scaling, and then this matrix that describes the contexts. So we have all the columns, all the contexts, and the rows are 2 dimensions. And you can guess what's happening in here. If I really have this thing and it really describes what's going on, then yes, these are the word embeddings that I want to read off, because they're selected such that if you multiply them with the context embedding, they tell you the compatibility. They give you these numbers of how often they occur together. And so this is the solution to the question of what is this word in terms of its relation to its contexts and in terms of its relation to other words that fit in these contexts. So SVD, if you really want to build up this huge matrix and run like a full SVD on it, yeah, that's going to be expensive. That's true. Which is one of the reasons why Word2Vec was nice, because Word2Vec doesn't do this SVD and instead does like a smaller mini batch gradient descent kind of thing. But just as like a theoretical thing, I think this is really nice to see, because it shows you that there's really no magic involved. There's nothing magical about gradient descent and about neural networks and all these things. We can really go from this simple matrix, apply this linear algebra decomposition, and boom, we have word embeddings that look nice like this. Oh, sort of. I think that's pretty cool. Maybe you don't think so. That's okay. You can join us again because we will be moving on. This will be what it would look like. So yeah, not great, but not bad. Dog and cat are close to one another. Cow is sort of there, but not that close, and green is far away. So that was fun. Hopefully, I thought so. But we're going to ignore that because we're going to do something else, and that is end-to-end learning. Instead of saying, oh, we're going to do this fancy technology to create a word embedding, we're just going to be saying, look, I'll initialize the word embeddings randomly for all words, and then just train on what I want to train on. Train on my task, do gradient descent, which I hope you have heard of and have done maybe in the past labs. And then through gradient descent, like backpropagating into the word embeddings all the way down, we are going to find out what good word embeddings are, and it's going to be fine. We don't need to think about it. That's sort of what we're going to be doing for the rest of this lecture. Yeah. So I should ask, how do people feel about gradient descent? Does that, as a concept, like initialize randomly, do gradient descent, get good parameters? Is that a pipeline that makes sense to people? That's a timid answer. Okay, some people. Okay, cool. So that's what we're going to be doing. So what we need to do now is describe our model, describe the end-to-end approach that we want to do. So here's a very naive pipeline that we're going to be building. And that naive pipeline is going to be bad according to all the things we've defined previously about languages complications, but it's going to be a start. You got to start somewhere, right? So we're going to start with a sentence and look up the word embedding for every word in the sentence. So now we have in this example 5 word embeddings. And what we're then going to be doing is just averaging them. That's not great, right? It's not great because we again made this bag of words assumption that there is no order and all the words are equally important. But hey, it's something. It is a very bad, but nevertheless, an embedding of our sentence. And using this sentence embedding, well, now we know what to do. We have seen how to classify from an image embedding or from some other embedding, right? We just take a linear layer or many linear layers. That gets us these scores for each of the 3 classes. So the linear layer has to go from the 2-dimensional embedding to our 3 classes. And these scores, we can already see negative got the highest score, positive got the lowest score. But you will see these scores sometimes called logits because we're not done here. We're going to be doing something else to go from these scores to actual probabilities, because probabilities are nice. And so what we're going to be doing is exponentiating the 3 scores. So that way, okay, nothing is negative anymore. That's good. And now we just normalize. We just divide by the sum, and we get probabilities. This operation of exponentiating all the individual scores and then normalizing is called the softmax. And it's an integral part of any classification pipeline where you want to go from scores to probabilities. You see that the probabilities reflect what we saw in the scores. But the good thing is that with these probabilities, we can train more easily because we just have to say, for example, if this was a negative example and we want to do training, all we have to say is make the negative probability go up. We can't do that for the scores, right? Because if we say make the negative score go up, you might just say, I'll just make all scores go up, and that's stupid. That doesn't help anybody. But if you want to make the negative probability go up, the other 2 have to go down. So probabilities are cool. We love probabilities. They're great. You can sample from them. You can calibrate with them. It's great. And we'll talk about that maybe a little bit later. But so this is going to be the end of our pipeline. We have managed to go from a sentence, averaging the word embeddings, doing 1 linear layer or maybe you do many layers. Maybe you have a whole multi-layer perceptron, full feed-forward network with lots of non-linearities in between. But you get out to these logits and eventually these probabilities. So what works about that and what doesn't? Well, the good thing is that it is end-to-end, and we can learn all of the parameters using backpropagation and gradient descent. And I really like this ending part of it, where we have a sentence representation and then just do a linear layer and a softmax, and we get probabilities. Because yeah, probabilities are awesome. But there's of course also bad, and that it's just not really solving our issues about interactions between words, right? Because we just averaged all the words, all of them equally important, not caring about order, and we've already established how that's a bad thing. So let's make this a little bit better, and let's jump straight ahead to a much more complicated model, but one that is really cool and actually solves these issues for us. So before we do that, maybe you had a question on this. Maybe this is something worth spelling out. With images, you could imagine having a fully connected neural network, right? You could imagine a fully connected network that looks at every pixel and just goes up from there. And convolutional layers really are a way to get translation variance and to combat like the size of the network. So that's nice and all. But for text, this is not going to work. Why is this not going to work? Well, we can't just concatenate all the inputs and then say, oh, this is our vector, now predict something from it, because sentences have different lengths. And so the vectors would have different lengths, and that doesn't work, right? Because our layers have to have fixed dimensionalities. So just if that's something you were thinking, it's not going to work out. We need something smarter. So the next attempt is going to be saying, look, we want to have some local interactions. Well, we know a tool for that. It's called convolutional neural networks. And so that sort of gets us the n-gram idea back in. If we do a one-dimensional convolutional layer, so the filters look at, say, in this case, just 2 adjacent words, and then produce 1 output representation, we do catch this bigram hardly amazing, right? And this is, sorry, the question, would an exponent's favor positive x values? Yes, that's right. So if you have a large score, this would be saying this is a high probability that this is the correct class. I don't know if that was quite your question. feel free to reframe. Anyway, so if we do these convolution layers, now we end up with a bunch of new representations that sort of represent these interactions between adjacent words. And now we can average those or do a different kind of pooling. We could do max pooling, whichever your favorite pooling is, and then get a sentence embedding out of that. That's already better than the previous one. And again, we can have similar considerations where we say, maybe this CNN filter looked at 2 words. We could have a filter that looks at 3 words, and that gets us trigrams and so on. Now, what is better about this over the n-gram version? What did we really gain so far? Because it sounds like we built an n-gram machine. So this doesn't feel like that much better. But what did we gain even now? I'll tell you, the models perform better, but why do they perform better? What's sort of the intuition for why this is helping us a little bit more? The context is the same as with the n-grams, right? We only look at small local context windows. But the good thing is that the n-grams were really discrete units. The n-gram hardly amazing and the n-gram not amazing didn't really share any information between them. So if you've seen hardly amazing a bunch of times with negative reviews, it doesn't tell you anything about not amazing. However, when you use word embeddings, if you look at the pattern for hardly amazing, and you know that the word embedding for hardly is going to be similar to the one for not, then it's reasonable to assume that even without having seen the phrase not amazing, you would know how to deal with it because it's very similar to hardly amazing. You've seen the similar thing before. So that's why this continuity, the fact that we turned everything into numbers, can be a great asset. Okay, so that is what we've gained so far over n-grams, which is nice. Better performance, not earth-shattering, but nice. And so I want to make sure that we kind of understand that point before we move on to actually doing something amazing with this. So what are your questions on this? If you have any. If you don't, okay, well, fine by me. You can just say in the chat how you feel about it. The averaging helps us in the sense that we need to somehow get to a fixed width representation, something that has a fixed dimensionality that we can then run through our linear layers, our nonlinearity, our softmax, and so on. Right? CNNs have been used for these things. And I wouldn't be surprised if people were using them today because they are a relatively simple way to do this. And sometimes catching like the local context windows, the n-grams is good enough. But we're going to be seeing the dominant paradigm on the next few slides after we feel good about this one. Yeah, that's a great question. How do we deal with misspelled words or names or anything? And that's sort of asking the question, what if you encounter a word that you have never seen before? You don't have a word embedding for it, do you? You don't know anything about it. And that's an actual issue. That's a really interesting issue that I'm absolutely not going to talk about now, but I would love to talk about after, because this is like so my research area. But yeah, it's an issue. So what people used to do, just very briefly, what people used to do is say we replace all the really rare or novel words that we haven't seen before with like a token that just says unknown. And so the model has seen lots of unknown tokens and doesn't completely give up on this word. It just doesn't really understand it. Exactly, this UNC token. So that's one way to do it. Another way to do it is to say, look, we don't want to use words. We just want to use characters and do everything on characters. That's its whole own sort of issue. And then you can say, well, what about subword units? And I'm already getting way ahead of myself, but please feel free to ask me about that later on. It's a great question. Okay, so how do we change words to numbers? We have seen a way that uses matrix factorization, but we said this is sort of an interesting way, but it's not the one that we want to focus on. We want to make our life simple, start with randomly initialized word embeddings and update them through gradient descent as we learn to classify. The softmax function is really the function itself. Oops, let me go back. The function itself is, this is the way it works in the forward pass that we exponentiate and normalize. And all these operations are differentiable, so we can also backward pass through the softmax. And you might know the softmax by different names. In fact, if you only have two classes, it turns out this is, anyone know what it is? Two words. If we have two classes, the softmax is just known as logistic regression. So you've already seen that. Right? It's the same idea, just the softmax extends logistic regression to multiple classes. Fun fact. Does that sort of help with these questions? Otherwise, feel free to ask again. Okay, so the remaining issue that we want to tackle is going to be looking at long distance. So we said there could be arbitrarily many words between the not and the amazing, right? But again, we only look as far as our little context windows, our little local windows go, our little n-grams that we capture with our convolutions. Wouldn't it be better, and I'm going to be dreaming for a second here, wouldn't it be better if every word could look at every other word? If all the words could sort of see each other, if the not could see the amazing and the amazing could see the not, no matter where in the sentence it is. If we could have these interactions between words, regardless of where they are in the position. And it turns out we can. And these interactions are going to be a little bit more complicated, but certainly possible. And so that's what the highlight of this lecture, in my opinion, is going to be, is finding out how that works. So the magic word is attention, or in our case, really self-attention. We want to have words attend to one another. So the sentence attends to itself, hence the word self-attention. This is coming, the variant of attention that we're going to see comes from this iconic paper, Attention is All You Need. So if you see all these da is all you need jokes in NLP, yeah, they're referencing this paper. It's not about the Beatles. And this paper introduced the transformer. And that model is what we're going to be building in the next few slides. So I'm just going to hit you with this. This is what we need in terms of our baking ingredients. Every word embedding is now going to be run through 3 different little linear layers. One of them produces a vector that's called the query vector. One of them produces a vector that's called the key vector. And one of them produces a vector that's called the value vector. Okay. Not worrying about what those mean just yet. Does this make sense? We have a word embedding, we run it through a linear layer, we get a different word embedding. We take a different linear layer, get a different word embedding, right? So we have 3 linear layers, one to generate queries, one to generate keys, one to generate values. Okay, so for every position in the sentence, we're going to have a query vector, a key vector, and a value vector. 3 word embeddings in a sense. So far, so good. Nothing scary happening just yet. So what are these vectors going to mean? Well, the names are hopefully somewhat indicative. The query vector is really our call out into the void, our thing like, hey, I'm looking for words like this. I'm looking for, so amazing might say, hey, I'm looking for words that look like negations, just in case. And then the key vectors are like, I look like this. So the word not might be, I look like a negation word. And so this way, the query of the word amazing and the key of the word not are very compatible, they're very similar. And so they will be very compatible and they probably want to attend to one another. Finally, the third vector is sort of what we want to output. It's the value, sort of what I have to say once you've found me. So the word not might be saying like, hey, I'm way somewhere else in the sentence. You don't actually, yeah, that's sort of a bad example. But it could be saying something like, hey, I'm a negation. Yeah, so you better think that your word amazing is like negative. So these three vectors are interacting with this in that sort of way, and we can write that in this iconic formula. I'm just going to break that apart piece by piece. What we want to do first is look at the raw compatibility between two words. So one word's query and one word's key. The compatibility is the similarity. How do you get the similarity between two vectors? Well, you could do cosine similarity, but we're just doing the dot product. If they're similar, they will have a high dot product. If they're very different, they will have a low dot product. Okay. Now, these are just raw compatibilities. And once again, we don't like scores, but we like probabilities. So what we're going to be doing is softmax these compatibilities over all the sort of search results. So the word amazing goes and asks every word in the sentence like, hey, what's our compatibility? So it has like a high compatibility with not, reasonable compatibility with movie, a low compatibility with the, and so on. And we have all these scores. And when we softmax it, we get a probability distribution. We get probabilities for how much to attend to each of the words. Okay, just the word amazing by itself. We're going to see this in an example in a second. Finally, what we're going to be doing in this formula, and that's what happens outside the softmax, is we're going to say we average the values of all our search results, so to speak, the values of all the words in the sentence. But we add as much of every value into our average as the probability distribution tells us. Okay, and so that, if you know your probability theory, it's an expectation, right? We do something under the probability distribution. So that's kind of nice. But anyway, and so that gets us now this average of all the values in the sentence. But it's not just a stupid average like we've seen before. It's an average where some words are more important than others. And it's an average that we get for every sentence, for every word in the sentence. That's the recipe. And that was a lot. So we are actually going to walk through this on an example. Let's take our little sentence here. The movie was hardly amazing. And I really just want to focus on the word movie. So this word, we have turned it into query, key, value vectors, all of that stuff. And we want to see, you know, what happens to this word. This word is now going to be allowed to look at the others and decide what it wants to be. Well, really take on the average of all the words in the sentence weighted by compatibility. So how that works is we need in green here the query vector for the word movie, and we need in blue the key vector of all the words in the sentence, including movie itself. Movie is allowed to look at itself. Sometimes, you know, you look in the mirror. I know, weird concept. But yeah, so all the words are allowed. So what are we doing now? Well, we said we want to have the compatibilities, right? So we take the dot products between every key and this query of the word movie. We get these raw scores. We softmax them. So that gets us a distribution that maybe something like 10%, 10%, 40%, 30%, 10%. I think that adds up to 100, something like that, you know. Words, and we average value vectors as weighted average according to the distribution. And the weighted average that we get is not an embedding for the whole sentence, but really just an embedding for the word movie. It's informed by all the other words in the sentence, but it still describes the word movie because it started off with the word movie. searching using its own query. Okay, so really we have only described sort of one column of this diagram, because this happens to every word. Every word is now going to go through this process. And you see, that's why transformers have quadratic runtime. Every word has to do this procedure where it looks at all the words in the sentence. Quadratic runtime. And so every word gets turned from a word embedding into a new word embedding. Now, it doesn't have to have the same dimensionality. Here I had it have like a bigger dimensionality, and that's fine. But this is, yeah, this is the self-attention step, really the heart of what I think is interesting about the transformer. Yeah, how do we feel about this? That was a lot. This is like the messiest slide in this deck, and I really hate it. But yeah, how do you feel? If bad, don't worry, there's just one more slide, and then we can all forget about this again. If you get the idea, I think if you get some sort of intuition, that's really all I want to take away from this. That's why I didn't do it all that mathy and in detail. But I think if you get the idea that every word looks at all the other words and then takes on information from them, that's really all that matters. Now, we're not quite done yet. This contextualized word embedding of sorts, this weighted average, well, it now contains a bunch of information, right? It contains this average of lots of things. And it's reasonable to assume that we want to give it some thinking time of sorts. So what we're going to be doing after this is just one last step where every one of those new averages gets to think for itself a little bit. So every one of those is just put through the same feed-forward network, multi-layer perceptron, linear layer, nonlinearity, whatever you want to call it, something that just operates on the small fixed width vector. And that gets us a new embedding for the word. And so what we've described here is really a pipeline to go from a word embedding to a word embedding, but in such a way that every word is informed by all the other words. That's really the main takeaway. And I think I have, yeah, this is the picture that I want you to just keep in mind for this. The transformer takes in all the word embeddings, mixes them all up in fancy ways, and spits out new word embeddings that are contextualized, where every word embedding not only contains information about this word, but also about the other words and the relation between those. Okay. Let's look at the chat. So you get the word movies different creations. Yes, exactly. So the original word embeddings, movie is always movie, right? But what gets up here is an embedding for movie in the context of the movie was hardly amazing. So it really tells us something more about the sentence. Yes, exactly. Okay. Yes, the presentation will be available afterwards. I'll totally, it's like a Google Slides doc. I'll totally have the link in the Discord or something. We'll sort that out, no worries. Okay, so this is the transformer model, more or less. It's not quite the transformer. We've omitted like a lot of details, like the fact that we actually have multiple heads of attention and that there's some layer norm stuff in there. And we have not talked at all about the fact that attention was not just invented by the transformer, but has existed before and it's been widely used in machine translation and so on. But I hope you kind of get the idea. The idea that this is a powerful model to turn sentences into contextualized word embeddings. And as you might guess, because you've seen neural networks, we can stack this. So we can do this once to get contextualized word embeddings, and then we're gonna do it again. And maybe we do this 16 times. And so these words really have had a long time to think about how they relate to other words. So we get some really interesting representations that way. All right, so that's going to be a transformer for us. And as I said, this was sort of the hardest part, the technical highlight of the lecture. So if you are despairing and have left your computer, please come back. We're going to do something now where we only need to look at a transformer as this black box that turns embeddings into new embeddings. what we're going to be looking at is, oh yeah, sorry, I should say, why did we do this? We wanted to do classification. This is like a complete afterthought to what we've done. If you have these things, you can just average those or take the first one or whatever, really. At that point, it doesn't matter. They've had so much time to talk to one another and think about it that all of them should have a reasonable idea of what the whole sentence is about. This is a negative review. So you could do all these things. Okay. So much for movie review classification. Let's move on to the big thing that I love, and it is language modeling, or how to generate realistic looking text. The basic idea is, instead of predicting a class that is like positive, negative, neutral, or sports, politics, we are going to be predicting the next word. And you all know this, right? If we use smartphones, we all know our predictive keyboards. This is a little screenshot I made yesterday, and I disagree with my keyboard here. I love making slides, but apparently my keyboard thinks I hate it. So we know it's possible to have like a thing where we have what we might call a prompt, something that is text that we've already written, and then we ask to classify, given this prompt, why is making slides. So given this prompt, tell me what is the next word going to be. And really, what is the next word going to be? Well, that's just another classification problem. It's a classification problem where the classes are all the words that we have in our lexicon. So we need to select a finite number of words. This is true. We can't generate new words like that. We need way more machinery for that, which is really fun, but no time. But we can pick out of this finite list of words the next word. And that's what happens on our phones, right? So that's really neat. And in fact, this is how you might want to do it with transformers. You have your sentence making slides is, and then you add another vector here in the fourth position. That's really just a dummy. And this token is often called mask, for something that's masked out, something that's not visible. And so if you run this through the transformer, hopefully the embedding that comes out in the fourth position is going to know so much about the previous sentence that we can run it through this linear classification layer that gives us the scores for every word in our vocabulary. And then we can just do the softmaxing and, I don't know, pick the highest one, I guess, right? That seems reasonable. If we just do this and we pick the highest one, yeah, we have generated a new word. And so we could say, okay, well, now we have 4 words and we put those in the transformer, and in the 5th position, we put the dummy mask in, and that allows us to classify the 5th word. Now we put 5 words in and we classify the 6th word, and so on. And so that's the way we have what is called an autoregressive model for text. Autoregressive, like doing regression on itself, sort of predicting from what has been predicted before. It's a left to right decomposition that we often use. First, we need to predict the first word from just a dummy. Then we predict the second word from the first inner dummy, the third from the first 2 inner dummy, and so on. Okay. Well, there's one little thing. We still need to actually predict to stop the sentence, right? Otherwise, the sentence would go on forever. And so in the end, we want to classify this end of sequence, end of sentence token, EOS, that says, all right, we're done here. You can stop generating now. The first can very much be a dummy, to answer that question. So when we start out here, we want to generate the first word. We don't know what anything is yet, right? So we really have a transformer that, imagine I cut this off here and really just go from dummy to, well, classify me something. Chances are the transformer is going to be like, I just see a dummy. It's just a dummy. I don't know. Start with V maybe, or A, or, you know, just something generic to start a sentence. I don't know. Or making if you want, really, it's possible. So it's very much something we can do and we have to do if we want to start from nothing. Or we can do what I did here and start from a prompt, something we've already written. And that can have a variety of uses that we're not going to get into very deeply. Okay. So predicting EOS, we're done. All right, is this enough to generate? Well, if you have ever done any of these like fun Twitter thingies where it's like, oh, type this into your keyboard and then let it complete the rest of the sentence. I don't know if any of you have done that. I think it's always great fun. Some people have some excellent things coming out of that one. And I did that here. Making slides is, and I was like, a good thing. Lol, lol, yeah, lol. I just clicked the, the best auto completion, and you see that it's not a great message. I mean, I would send this to my partner, maybe fine, but not to anyone else. It's not quality text. So really always picking the highest, the most likely option is kind of boring. And if you think it through, if we were to do this from the very start, your language model could really just give you one sequence, namely the single most likely sequence. And that's boring. We don't want that. We want to have something else. We want to sample. Oh, did I say sample? Would you look at that? We want to sample lots of different sentences. We want to see lots of possibilities that are all grammatical. Because in language modeling, there really isn't just one correct answer, right? Where a movie review might have one correct answer, positive or negative. In language modeling, we don't have that. A sentence can start so many different ways. And so we really want to spread our probability mass. And if we look at our model, if we look at what we did, we have that. We have a softmax, and the softmax means a probability distribution, right? Like maybe indicated by that on the right, where like half the mass is on good, and then a little bit is on bad, and then a mediocre amount is on amazing or something like that. Yeah, that's the probability distribution we get from our next word classification. And since it's a distribution, it describes a random variable, and we can sample from that. So that's what we can do. Instead of taking just the highest word, sample which ones we want to take. And so now it's time to show you this example of a text that was generated from GPT-2. This was a big deal when GPT-2 came out, a big transformer-based language model, much like the one that we've built in this lecture. And it generated this text by sampling, not always taking the single best answer, but sometimes taking something that's not the best, but still reasonably likely. And so this is a very nice visualization that shows when something really strange was chosen. So the green ones are all like, okay, predictable, that was pretty likely. Yellow ones are a little bit unlikely. The red ones are very unlikely, and the purple ones are incredibly unlikely. So we see that in a shocking finding, scientists, yeah, that's a little ungrammatical. Okay, discovered or heard of unicorns. That's surprising. And from there, the text goes on. It's a really fun read. It was a really iconic example because it shows an astonishing feat that was not possible with old school language models. And that's this long-term coherency between like starting to talk about unicorns here and still talking about unicorns down here. It was a big deal. That's all I'm saying for this. So yeah, and now you know how it came to be. Now you know what really happens. It's a transformer. It takes in word embeddings, and we predict the next word, and we sample from the softmax. And yeah, that's all I have to say about that. We've seen very much a quick crash course into text classification, and going from classification to all sorts of neural architectures up to language modeling. And in language modeling, we've seen how to generate actual new text. So I hope you're really excited about this stuff because you're going to be seeing it in the lab, I think, tonight, this afternoon. So that'll be fun. Anyway, this is kind of what I had in the way of slides that I absolutely wanted to get through. And I think we are actually really good for time. While I was going to be like, so please pick one of those topics and we can talk about that, I don't actually know if we're going to have time for that. So maybe it's easier if we just have it like as an open Q&A, and you can ask questions in the Zoom, I think, has a Q&A, or in the chat, and we can talk about things from there. So I see one question that was in the Zoom QA. How do we get text to speech ML algorithms to correctly pronounce non-phonetic words? So what do you mean by non-phonetic words? You can unmute yourself if you want. If you're around. Otherwise, I'll come back to that question when we. You can just post in the chat also. Yeah, any other questions people have, or any other topics they're interested in? I mean, you can just say, hey, tell me more about this or that. The last slide, the characters were highlighted red. You mean something like this, right? Yes, that's a very good point, and that's a really interesting thing, because as I said, having a finite vocabulary, having only so many words is kind of restrictive, right? You can't ever generate a new word. And so what people do instead is say, let's have our tokens not be words. Let's have them be parts of words. Some tokens are so common that like they are just one word, like the word fact. I bet that it's just one token. But here we see, for example, unicorns is broken up into at least two tokens, unique and orange. So this would allow the model to compute, to create entirely new combinations of words. For example, we could combine this unique with, let's see, where's another word piece? Oh, here, Andes Mountains, unique with ES. So we have unices. I mean, that's not a word, but maybe, hey, the model could generate it if it really wants to. And we see in the case of OV tier that these word pieces can be as small as a single letter. And so that way, we actually can generate entirely novel words, which is really amazing and really fun to look at. And we do it without having to go all the way down to characters. We can still maintain words for these more common words, and that saves a lot of compute and a lot of data. Okay, lots of questions coming in. Excellent. Let me see. When did I start my NLP path? I started in 2016, really, I would say. Yeah, 2015, 2016. As I said, I was more doing formal language theory stuff with grammars, automata, parsing, got into translation, got a life-changing internship where I learned about real research, and I was hooked. And then I did a bunch of other stuff. The predicted characters too. We talked about that. How are words with multiple meanings handled? Oh, that's a fun question, because really we just don't care, kind of. In word embeddings, as we've seen them, like as their standalone word embeddings, where every word, every word is somewhere. Well, there's really no way to handle it, right? The word bank is similar to institution, but it's also similar to sand or something, right? It's the classic example of two meanings. And there's really no good way to do it with word embeddings like that. However, we do have the hope that contextualized word embeddings, such as they come out of the transformer, that they actually can disambiguate, and they say that like Chase Bank, and you're like, okay, so bank must be the financial institution. So let me output the word embedding for bank, specifically the one that is financial institution. So that's something that we hope these contextualized models can do for us. Count vectorizers, are they used in here? Sorry, I don't know what you mean by count vectorizers. Maybe you can elaborate on that. Model architectures like GANs be used for predicting misspelled words. That's sort of an interesting one. I also see that someone asked in the Zoom Q&A how to deal with misspelling, and maybe that's something interesting to talk about. If we have words, then yeah, the issue. It would like to answer this question live. Do you want to talk about that?
Oh, no, sorry. I'm just marking this as something you're
Oh,
in,
okay.
really.
Gotcha. No worries. Yeah. So how do we deal with misspelling? Yeah, if you have everything be a single word, then a misspelled word is just going to be like, new word, I don't know, unknown, which obviously is not what we want, right? So if we do word pieces, then a misspelled word often gets broken up into multiple of these word pieces, which is not great, but at least you can maybe piece it back together. Again, the hope is that the more complex and complicated our model on top of the word embeddings is, the more likely that it can piece together the meaning. The more likely that it can say, well, the word says this, but I really think in context, it makes sense that they meant that instead. And so for common misspellings, for common typos, I think these models have a pretty good idea of what's going on. Of course, the best models, as far as I know, to deal with misspellings are models that really are based solely on characters. So we don't have word embeddings, we have character embeddings, and all the characters are used one after another. Now that's really expensive because again, we have quadratic runtime and all of these things for transformers, but it does kind of buy you a little bit of that. Other things you can do, of course, is do some pre-processing. You could say, we check for every word, is it in the lexicon? And if not, is there a very similarly spelled word in the lexicon, and we replace it. That would be one very cheap way to handle it. But the issue is you might actually overcorrect. You might correct things that were supposed to be misspelled because they're novel words. For the second half of this questions, using GANs is actually a tricky business. For images, it's a little bit easier like to apply a GAN intuitively, because what you want to do is you want to say, oh, well, this pixel should have looked a little bit more like that to fool the discriminator, right? So we can't really do that with text. You can't say this word should have looked a little more like that, like, because again, words are discrete units. So that makes it really hard, and people have for a long time struggled to use GANs for NLP. Now, I think some of these struggles have been ameliorated somewhat, and there are useful uses for GANs. There certainly is a lot of adversarial training that is happening in a bunch of NLP tasks. That's something interesting to talk about. Okay. Oh, really nice question. Oh, hey, no worry. I wish I could show you the cute rabbit that I'm petting. Maybe if it climbs on my shoulder. In the previous lecture, we talked about going from image classification to captioning. So captioning is something that we can also do with the models we've done today, right? Because captioning means generating text. So if you want to generate text, well, we know how to do this. And what we really want to do is have our prompt be not just whatever maybe we have as text prompt, but also the image. So what we could do is take the transformer and feed in the image as a vector as well. And then we could just use the architecture that we've seen and generate the caption from that. And as long as we train the model well and generate these captions from there, that should work out. I hope that sort of answers the conceptual level question. Okay, what about sarcasm detection? Oh, that's tricky, and I honestly have no idea how that works. Yeah, sorry. I know people are researching it. I know there are entire workshops on this kind of stuff, but I really don't know what's like the current way that people do this generally. Sorry. If GPT-2 produce that with a transformer, yes. So the GPT stands for generatively pre-trained transformers. We didn't talk about pre-training at all, God, but so they all use transformer architectures that are very similar to this. They have a slightly different connectivity pattern to make it a little bit faster to run in parallel. And they have lots of layers, and then GPT-3 does a lot with like sparsity, but it's all based on this idea of transformers. So if you look at these papers, this should look very familiar to you. Slang and regional dialect. I think that would also be considered something like misspellings, where you're like, oh, this looks like that word, unless it's like a slang term that has nothing to do with it, in which case, yeah, it might be an unknown word. And that's a lot of the reason also why there is a lot of injustice in NLP technology, because a lot of the technology, yeah, it works really well for like white American English. Okay, great. And then it doesn't really work for people with accents or speakers of AAVE, right? Okay, are you doing all right there? Okay, sure, climb into the desk. And so that is actually a really big issue, that we don't know how to adapt to these things and how to really deal well with them. Come out here. Let me just put her down. TF IDF. Oh yeah, okay. Let me go back to the comment for other questions. Are they used in here? So TF IDF can be enormously useful. Also, I realize we're going over, so just shut me up at any time if you want to cut to office hours, because I can just keep going all day. So TF IDF can be really useful if you don't want to do something neural, if you just want to do something information retrieval, like TF IDF is still amazing, right? Just like BM25 still gets you a lot of the way. But it can also prop up in really unexpected places. So we had a paper last year where we wanted to do topic modeling. So taking text and figuring out what are the topics and what words belong to which topics. And we did this through clustering word embeddings, essentially. But we still weighted the ones. We said some words are more important than others in this clustering process. And we did that using TF IDF. So there's absolutely a space for these methods in NLP, and they can still be very useful in many ways. Yeah, okay, I see the second part of the question. Something we can also do, and that is done in some applications, in particular in topic modeling, I know it used to be a thing, is removing stop words, is what they're called. Stop words being words that we think are not really useful for our analysis, like the and is and a and then and stuff like that. And TF-IDF might help you find these stop words, right? It might help you find words that appear everywhere but are not indicative of anything. So definitely that can be a thing, and that has been done a lot, especially more in a historic context of NLP. These days, people do like putting in the full information, not deleting any words, not doing any like stemming, lemmatization, any of that, as long as we have models that are powerful enough to cope with this variation, which for the most part we do. Yeah. How do we deal with special characters like quotations, exclamation marks, and so on? So when I was talking about our sentence in the beginning, I did kind of cheat, right? When I said we have a sentence, the movie was hardly amazing, really, and I said this sentence has 6 words. Well, usually what you would do is you pre-process the text and split the punctuation off of the words so that the sentence would have 8 words. The movie was hardly amazing, comma, really, period. And you could even say it has yet another word that is end of sequence, right? So we use, or like what is nowadays called pre-tokenization, but for the longest time used to be called tokenization, is really this question of deciding how do we go from text that is a stream of characters to a sequence of these bigger tokens, these bigger units. And yeah, so splitting off punctuations was one of the things people did in that. But also lots of other neat little tricks, like, okay, for example, what do you do with a single quotation mark, right? Do you split that off? Well, I mean, it could be part of, like, say, an Irish name, so you don't want to split it off. These things are really complicated, right? Or like, does a sentence end after a period? Oh, not really, right? Because we have like Mr., Miss, Mix, all these things. So maybe some abbreviations have different treatments. And so there used to be all these complicated side things. And it is often been considered the bane of NLP, the old topic of tokenization. People hated it. So people are very excited these days about models that don't do any tokenizations and that actually just work on characters and bytes. If you're interested in that sort of thing, I will completely unashamedly plug something that we just put out as part of the Big Science Large Language Models workshop, which is a survey on exactly these questions of tokenization. I'll just put that in the chat. We didn't talk about it, but it might be a fun read. Oh, this is for hosts and panelists. I need it for everyone. There we go. Okay. Cool. Well, let's see. What else do we have in questions? In Zoom Q&A. What kind of languages are challenging for NLP? That is a great question, because believe it or not, I have written papers on this. So this is sort of an interesting question. Are there languages that models struggle with more than others? So there are some hypotheses we have what might be hard. And one of those things always used to be a very rich morphology. So yeah, having words be, sorry, I also think I need to charge my laptop. I might just die any second. So if I'm gone, it's going to be goodbye. But one thing that might be hard is morphology. So having words that have inflections. In English, we don't have much of that. We have like, I run, you run, he, she, it runs. Okay, there's an S at the end. But we don't have that much of that. There are languages that have a ton of this. All right, yeah, Russian, of course, being a very morphologically rich example. My own native language, German, also has a fair bit of morphology. And that can be tricky, because suddenly there are so many different word types, all of which are used and important to see, but you need to have a huge vocabulary to have them all. And you really want the model to generalize, to look at those as the complex compounds that they are. And that can be hard. It has gotten a bit better. Again, with character level processing, you get a lot of that for free. But there are also other things. So in our research, we, for example, found, and you can look at this if you want, or message me and I'll send you links. We, for example, found that there is probably a link between the average dependency length in a language and the difficulty of modeling this language. So average dependency length being, if I have two words in a sentence and they sort of depend on one another and interact with one another, are they far away or are they close by? And languages differ in their average dependency length. And we found a weak correlation, I will say, with modeling difficulty there. So these are all sorts of things. If you're interested, look at this paper that we wrote. Most of it is really not linguistically interesting. Unfortunately, we found that there's a lot of like technical factors that make languages hard rather than linguistic factors, but it can still be a fun exercise, I'm sure. Okay, last question. Are there different levels of complexity that can be achieved depending on what languages compared to English and training? Ah, interesting. So this kind of is a similar question, I guess, on whether languages differ in how easy it is to generate in them. I will say that we are pretty good at English generation, far better than we are at, say, German generation. So it will make sense that you would have an easier time passing a Turing test in English, although in this specific example, past approaches have been just to make a model that is on purpose making mistakes to fool the examiner into thinking that it's someone who is unexperienced or young. So I don't know. It could be any of those things. But yeah. Cool. I think that's all the questions we got through. So my laptop has 4 minutes of battery left. Amazing. Let me show you the cute rabbit.
Okay, I think Sabrina might have frozen or her laptop died, but thank you so much, everybody, for joining us, and we'll see you in office hours soon. Bye, everyone.